Thanks, Ewan, for the introduction. It's a pleasure to be here on a nice, beautiful Saturday morning. Are you going to get outside today? I hope so. I wanted to start with a little quiz, just so that I know who I'm talking to. In mathematical biology, one of the things that MBI tries to do is look at how mathematics helps you to solve problems in biology, but also how problems in biology affect mathematics. And what I'm hoping this morning is to try to go in both directions. So first of all, how many of you have had a course in differential equations? Great, okay. Algebra? Okay. Neuroscience? Not bad. Okay, so I have to be careful what I say. In any case, I certainly have the background for this talk. What the talk is about is patterns of phase shift synchrony in periodic solutions. So I imagine I have a differential equation and a periodic solution to it, but not just any old differential equation. It's going to have some structure, as you'll see, either networks of differential equations and symmetry. And what is phase shift synchrony? Well, the best way I can demonstrate it is to walk. Think about walk as a repetitive periodic gait. And what happens if you swap legs? Well, it's a little hard on your legs, but other than that, when you do this abstractly, you're going to be in the position that you would be in a half a period later in the gait. So swap legs, I've switched the position of, of my legs, so that's the you're a half period out of phase. So this is what I mean by phase shift synchrony. It's not actually synchronous, it's not doing exactly the same thing, but when I swap, I'm half period out of phase. Now, quiz, what's the gait that when you swap your legs, you have a zero phase shift? In other words, you're really doing synchronous motion. Hopping? Yeah. So do you want me to demonstrate? No, don't ask me to. So hop or jump is a gait where you're moving both legs in synchrony. So the talk is going to be about how you find these kinds of periodic solutions with prescribed spatiotemporal symmetries or phase shift synchrony. I'm going to use two examples, quadrupedal gaits, so four-legged animals, they're gaits. And there the idea is that biologists believe that there is something called a central pattern generator in the nervous system somewhere. And for primitive animals like a lamprey eel, they can absolutely find the neuron which is bursting in exactly the cadence of the swimming gait. So they believe that there is something called a central pattern generator, and the central pattern generator controls the different gaits. Is there such a thing? There's a lot of evidence that there is, even in mammals. But let's take the mathematical road. Let's assume that there is such a central pattern generator. Well, animals do some standard gaits. They walk, trot, pace, four-legged animals, bound, gallop. What does this tell you about the central pattern generator if you know that if animals do these gaits? The second example is something called binocular rivalry. How many of you have looked at visual illusions? Okay, if you haven't, go on the web and just Google visual illusions, and there's some remarkable ones on there. Visual illusions is a place where you can't, from the information you're given, you can't actually decide what the original image is that you're looking at an image. You can't decide what the actual image is, and your mind lets you alternate back and forth between possibilities. Binocular rivalry is something which is similar. You show a subject two different images, one to the left eye, one to the right eye, and then ask the subject, what do you perceive? And, well, symmetry and the spatiotemporal symmetries or phase shift synchrony are going to appear in this example as well. Okay, so let's start with the simplest example of what I have in mind from a mathematical point of view. This little graph is supposed to evoke in your mind two systems of differential equations that are coupled. Because the circles are the same, they're identical systems of differential equations with identical coupling. So this graph corresponds to a collection of differential equations. x1 dot is f of x1, x2. X1 is the internal state variable of node 1, x2 the internal state variable of node 2. And the fact that these are identical says that x2 dot is f of x2, x1. Well, it's not surprising that when you look at this, that there's a symmetry. If I have a solution, x1 of t, x2 of t, and I swap coordinates, x2 of t, x1 of t, that's also going to be a solution to this system. So what a symmetry of a differential equation is something that takes solutions to solutions, definition. And this swap is such a solution, is such a symmetry. I claim that the symmetry sort of enables you to point to two kinds of periodic solutions. One where the two nodes oscillate exactly in synchrony, so x2 of t is x1 of t, and the other where the two nodes are a half a period out of phase. This is exactly the hopping and walking that we were talking about before. So let's do a little bit of group theory with differential equations to see what's going on. Suppose I have a periodic solution in some large dimensional system. I'm not worried about what the system of differential equation is, but it has a group of symmetries, gamma, and let gamma be one of these symmetries. And in this context, symmetries are just linear maps or matrices on the phase space. Then suppose that gamma takes x of t, the trajectory, picks it up and just plonks it down on itself. Then if gamma is such a symmetry, gamma x of 0 must lie on the trajectory somewhere. So it's x of theta t, where capital T is the period of the periodic solution. Theta is between 0 and 1. You have two solutions, gamma x of t. This is a solution because gamma is a symmetry. And x of t plus a phase shift is always a solution for an autonomous system. They have the same initial conditions, therefore they're equal for all time. And this is the space symmetry. This is the phase shift. Together, gamma and theta are a spatiotemporal symmetry of the periodic solution. So let's think of the simplest example in this collection of differential equations up here. If we know that swapping 1 and 2 is a symmetry, suppose I apply the swap twice. Well, then I would end up with x of t. It's going to be gamma x of t, which is x of t plus theta t. Apply gamma again, I get x of t plus 2 theta t. So x of t plus 2 theta t must be x of t. So therefore, theta must be congruent to 0 mod 1. It's either 0 or a half. If it's 0, you get the phase shift, you get the synchronous solution. If it's a half, you get this half period out of phase solution. So a very little bit of symmetry added to differential equations. It helps if you know behind all of this is uniqueness theorem for differential equations that makes this work. Now, most of you have taken a course in differential equations. How do you find a periodic solution to a system of differential equations? The answer is exactly correct. You can't find a periodic solution to a system of differential equations unless it's made up homework exercise. You're never going, you can find it numerically, but you're very rarely going to be in a situation where you can analytically write down a formula for a periodic solution. So how do mathematicians, especially applied mathematicians, go about finding periodic solutions in models? They do it primarily through a theorem called Hopf bifurcation, the Hopf bifurcation theorem. I'd like to explain to you what's in that theorem. So the way to do it is to start with a very simple system of differential equations, a planar system. It has a linear part and a cubic part. The linear part dominates near the origin. The cubic part dominates away from the origin. What's the cubic part doing? It's just pointing in towards the origin. The vector is pointing in towards the origin everywhere. The linear part, lambda is a bifurcation parameter. I'm going to vary lambda. When lambda is negative, well, this matrix has eigenvalues lambda plus or minus I. When lambda is negative, if I forget about the cubic term, the solutions are just going to spiral into the origin. If lambda is positive, they're going to spiral away from the origin. Well, then, if you look numerically, it's not surprising that when lambda is negative, solutions just go into the origin. They either go in linearly just along the rays, or they spiral a little bit, but put the two together, they're still coming into the origin. So this phase portrait, it makes perfect sense when lambda is negative. But when lambda is positive, you have a competition between near the origin, you're spiraling out, away from the origin, you're spiraling in. The way this balances off is that there's a periodic solution. So that's a kind of numerical analysis proof of what's a Hopf bifurcation. For this particular equation, it's actually fairly simple. If you look at our, go to polar coordinates and look at r squared, r dot is going to be lambda minus r squared times r. This equation is set up so that when you go to polar coordinates, it looks nice. And when r is square root of lambda, when lambda is positive, r dot is 0. That means you just stay on the same constant radius from the origin. That is, you have a periodic motion. Okay? So there is a unique periodic trajectory, which is small amplitude. In fact, the amplitude is square root of lambda. The Hopf theorem says this is perfectly general in the following sense. Suppose I'm giving a system of differential equations, many dimensions, which has an equilibrium at when lambda is 0. Suppose the Jacobian matrix, so this big n by n matrix, has a unique pair of non-zero, purely imaginary eigenvalues. Well, in this case, the eigenvalues were, well, it's going to be 0 plus or minus I, so it has purely imaginary eigenvalues. And all of the other eigenvalues are off of the imaginary axis. Then the theorem is, generically, there's going to be a unique branch of small amplitude periodic solutions that emanate from the origin. So in short, that very simple equation is mimicked in many dimensions as long as you know something about the linearization. Can I write down a formula for the solutions? No. Do I know they exist? Yes. And that's what I'm looking for. Okay. So let's go back to this two-node example and ask, well, what does the Jacobian look like if I have a synchronous equilibrium, say, at the origin? So at some lambda naught, f of 0, 0 is 0. Then the Jacobian is going to have the form alpha, beta, beta, alpha, where alpha is the derivative of f with respect to the first set of variables, the linearized internal dynamics. Beta is the linearized coupling, a derivative of f with respect to the second variables. And since you swap the variables, you swap alpha and beta. Now, it's very easy to see that xx and x minus x are invariant subspaces for this Jacobian matrix. That is, j times xx is just alpha plus beta times x, alpha plus beta times x. So x goes to alpha plus beta x on this subspace. J of x minus x is alpha minus beta x minus alpha minus beta x. Again, x minus x is a invariant subspace. If you're thinking of Hopf bifurcation, if the critical eigenvalue of j comes from alpha plus beta, then you will get synchronous periodic solutions in Hopf bifurcation. And the reason is that x2 of t will be approximately x1 of t. Alpha minus beta will give critical eigenvalues. The critical eigenvalues will give these half-period out-of-phase solutions. And this follows because x2 of t is approximately minus x1 of t. And if you think of if these were sines, sine of half a period phase shift is the same as minus sine. And this is approximately what's going on here. OK, so in short, in this kind of system, there are these two invariant subspaces. And something that I learned early on, if you do a big calculation and the answer is 0, there better be a good reason for it. It just doesn't happen accidentally. That you get an invariant subspace for this Jacobian matrix is not going to be an accident. So I'm going to spout some words which you may or may not know depending on your backgrounds. XX and X minus X are the irreducible representations of the group Z2. There's a trivial representation and a non-trivial representation. And what you're picking up are these irreducible representations that are associated with the group Z2. So now you need to know a lot more algebra than just a first course in algebra to see this. But there is a reason behind all of this. OK. So now that's the mathematics that I wanted to do up front. Let's have some fun with animal gaits. Oh, I forgot to ask you, how many of you ride horses? OK. 2? This is, yeah, I don't ride horses either. But this is, if you know, once you know this, I think you'll have more fun going to the zoo and looking. So four-legged animals walk, pace, trot, bound. So what are these gaits? Claim that they're described by symmetries, just like walk and hop, or for bipeds. In a walk, it's a 4-count gait: left rear, left front, right rear, right front. Okay? Got that? If you actually look at an animal walking, it takes you a little while to figure out what's going on. And it really helps if you know in advance what you're looking for. Let's look at the trot, which is, that's a kind of fun gait. Squirrels, small dogs will tend to trot. Left rear, if I may, right front, move synchronously. Left front, right rear move synchronously, and the two diagonals are a half a period out of phase. Got it? Okay, now see if you can pick up the left front, right rear. Okay, slow motion. Right front, left front, right rear. And they just hit absolutely synchronously. Legs are hitting the ground. So can you see this? Do you want to see it again? No? OK. And what's remarkable is how regular this really is. So I would argue that any model for gaits must really come to grips with the synchrony and phase shift synchrony. It's a real part of the problem. Pace, both left legs, both right legs, both left legs, both right legs. Long-legged animals like camels and giraffes tend to pace. Short-legged animals tend to trot. I've never really found out why, but I always think of it as long-legged animals, if they try to trot, will trip over their own legs. So there's a real, there's a good reason for wanting to pace. Bound, both legs, front legs hit the ground time 0. Rear legs time a half, just back and forth. Go out, look at the squirrels after the lecture, and they'll be bounding. Pronk. Anybody know what a pronk is? Now, I like giving this lecture, as I guess is obvious. One of the things that I like about it is people often come out, but prunk isn't a word. Now I can say, what do you mean it's not a word? There it is. All four legs move together, and small deer will do this. Garfield also does it, but small deer, and it's a lot of fun when you see this. Okay, those gaits have some symmetries. And I'm going to use this permutation of legs to describe it. In the trot, remember it's the diagonals that are moving synchronous. So if I swap the diagonals, I have a half-period phase shift. So swapping left and right legs will swap the diagonals, give a half-period phase shift. Swapping front and back legs, half-period phase shift. They swap the diagonals. The pace, both left legs, both right legs, swap left and right, half-period phase shift. Swap front and back, 0 phase shift. They're moving synchronously, the front legs with the back legs. Walk is this figure 8. Swap left rear to left front to right front, and you have a quarter-period phase shift. Okay. Well, now for the neuroscience, a very small part of neuroscience. Hodgkin and Huxley got a Nobel Prize circa 1960, I think, for work that they did circa 1950 on writing down a model for a neuron, a differential equations model for a neuron. I don't care what that system of equations is for the purpose of this talk. It's just that there is this four-dimensional system of differential equations that it does very well at modeling the bursting activity of an individual neuron. Remember I talked about these central pattern generators, which were somewhere in the nervous system. Well, a central pattern generator is supposed to be a collection of neurons. So it's a coupled system of differential equations from a mathematician's point of view. Suppose I had 4 neurons coupled together, synapses and so forth. That's going to be a 16-dimensional system of differential equations. And I don't know about you, but I'm not all that keen in trying to solve a 16-dimensional system of differential equations. And more likely, the central pattern generator has 100 neurons in a mammal or some large number. It's just a huge system of differential equations, and you're not going to get anywhere if you just plug it on the computer, although a lot of people do that. So the question that we wanted to set out to ask, we being Jim Collins, Ian Stewart, Luciano Bono, and me, some years back now, was what is the simplest architecture for a central pattern generator that will produce periodic solutions which have the same synchronies as walk, trot, and pace, that it can produce those 3 gaits. So it was a modest attempt to understand how the fact that we know that quadrupeds do these gaits, what is this going to tell us about the architecture of the central pattern generator? Now, it's a long story. I'm not going to go into that part of the story in the lecture today. But the answer is that this 8-node example is the simplest network that will produce walk, trot, and pace, or produce periodic solutions with those symmetries. You can see it's not a surprise that this network is there, because if the system produces a walk, then it should have this 4-fold symmetry in it. So Z4, and that 4-fold symmetry is the action is 1 goes to 3 to 5 to 7 back to 1, 2 to 4 to 6 to 8 back to 2. So that's the permutations that correspond to the walk symmetry. The pace and trot it's going to have at least bilateral symmetry of the animals, 4-legged animals. And the bilateral symmetry is just swap left and right. So this is the simplest network, which has Z4 cross Z2 symmetry also. but it does produce walk, trot, and pace. Now, how do you find these kinds of periodic solutions? Well, I'm going to assume that there is an equilibrium which is maximally symmetric. So all of the nodes have the same value. And I'm going to ask for Hopf bifurcation, what are the possible what's the Jacobian look like for a system of equations that's coupled in this way, and what kinds of periodic solutions do you get? Well, it's actually not, I haven't set it up completely at this point, but it is certainly a calculation that one can do with a first course in group theory. And there are 6 different kinds of Hopf bifurcation that will occur. One of them leads to pace, another to trot, and a third to walk. And that's what we were assuming in getting this network together. The fact is, it also produces a pronk and a bound. Well, that doesn't sound so bad. These are known gaits, so it's perfectly reasonable that it should do this. And surprisingly, certainly to us, there was another gait which we called a jump. And I want to explain what that gait is. So first of all, let's look at the trot. The trot is going to come, the full symmetry group is going to be a symmetry group of the periodic trajectory. That's the H symmetries that I had on one of the first slides. So every group element is going to give the same solution, but with a phase shift. Well, what are the phase shift zeros? Those are the kernels of the action of H. And if for a trot, the kernel is going to be Z4 of kappa omega. So what does this mean? Kappa says go across, omega says go up. So x1 and x4 must be the same, if that's the case. Across, up, across, up. So all of these must have the same waveform. Similarly, the x2s, x2, 3, 6, and 7 must be the same. And if I swap left and right, that's not, that has a non-zero phase shift, but kappa squared is the identity, so it has to, the only thing it can have is a half period phase shift. So x1 of t, x2 is going to be x1 of t plus a half. Notice, I should have said this earlier on, in this network, 1 sends its signal to the left hind leg, 3 to the left foreleg, 2 to the right hind, and 4 to the right fore. And in this, these 2 nodes are synchronous. These 2 nodes are synchronous. Those are the diagonal legs, half period out of phase. That's why this is called a trot. Okay? This is what's going on. Now, the solution that we found, that was a surprise had a kernel Z2 of kappa. So x2 equal to x1, x4 equal to x3, and so on. And now when you apply the fourfold symmetry, x1 of t, this must be, x3 must be x1 of t plus a quarter. And x1 of t plus a quarter. So we know a caricature of the gait. That is, when the animal will come down front legs at time 0, synchronous, rear legs come down at time 1/4 through the gait, and then 3/4 of a period later, the animals hit the front legs hit the ground. Now, Yuan was very nice when he introduced me. He mentioned that I was in Houston for many years. I don't know how many of you know what the cultural event of Houston, Texas, is during February, and text is bigger than monkey there. That's one of the scrambled images. And there are 4 images, 4 possible percepts that would come out of this Wilson network. And the 2 periodic solutions will be, indeed, alternation between the mixed images and alternation between the reconstructed images. So this idea that Wilson had applied to his networks using some symmetry analysis gives exactly what was observed in the experiments. So I'd like to work through this next example. I don't want to tell you what the answer is. Let's just see if we can figure out, using a Wilson network, what you might expect to see. So the two images, how would you describe the image on the left? What properties are dominant? There's a grading direction. This is a vertical grading, and the one on the right has a horizontal grading. So grading should somehow be important. What else? You mean this? That's the same in both images. Oh, there's these two. Yeah. That is, I don't think people actually see that part of it. What they see is the interior, and this is dominant in the experiment. But you're absolutely right. I just missed that. Anyway, that's not going to be part of the experiment. Let me just jump forward. The colors. You need in each image two colors. In the left image, there's gray and pink, and the right, it alternates green and gray. So to describe these images in the interior, and thanks for pointing that out, I'll have to keep track of that. You need to keep track of three properties. So let's take a Wilson network which has a grading direction and two colors. Now, what was the left image? Gray and pink with a vertical grading. So vertical grading, gray and pink. The levels are pink, gray, and green in these two columns. The horizontal grading had green and gray. And you get these excitatory couplings, these triangles that are in there. Now, what symmetries does this network have? It may not be so obvious to begin with, but if you swap these triangles, that is, swap 1 and 2, 4 and 5, and 6 and 7, that will be a symmetry of the network. After you do this, you'll get exactly the same network back. If you try to swap these two columns, well, you can do it if you swap 3 and 8, which have nothing to do with the triangles, swap 4 and 6, and swap 5 and 7. That will end up giving you another symmetry of this network. And then, of course, you can multiply the two symmetries together. Now, suppose that you have a Hopf bifurcation from a synchronous solution, as synchronous as possible, then, and rho acts trivially. 1, 2 acts trivially. Then the phase shift between 1 and 2 will be 0. That is, you'll have a fused state. So rho must act non-trivially in order to get a non-fused state. Similarly, rho tau must act non-trivially to get a non-fused state, and therefore tau must act trivially. Well, the maximally fused state is going to be 1 equals 2, 3 equals 8, 4 equals 6, and 5 equals 7, and 4 equals 5. And this is the colors code the maximally fused state in here. And we can ask, well, what happens if we get a Hopf bifurcation where tau acts trivially and rho acts non-trivially? It's going to have this form. The 3 and 8 nodes will be synchronous. The 1 and 2 nodes will be a half period out of phase. 4 and 6 will be synchronous. 5 and 7 will be synchronous, and these will be a half a period out of phase. So this is the kind of structure a periodic solution corresponding to a non-fused state would have in this model. And if Z0 is bigger, if Z0 is less than Y0, then you're going to end up with how should I say, 4 and 5, a half period out of phase, 6 and 7, a half period out of phase. You're going to go back and forth between gray and pink and gray and green and gray, and go back and forth between vertical and horizontal. And that's the two images that you started with. If Z0 is bigger than Y0, that is, you choose 3 and 8, then you will get an image which is pink and green together, going back and forth between vertical and horizontal. This is what the experimentalists found. You get these two images, not surprising. These are the ones that people were shown. But what people perceived, what they called color misbinding, and you get this back and forth between this. And it comes out of these Wilson networks with the symmetry analysis. Again, the differential equations themselves are not so important. It's the structure of the equations which seems to give this. Okay, now, when I started the talk, I mentioned that MBI, we like to talk about how mathematics tells you something about biology, how biology tells you something about mathematics. Well, implicit in what I've been doing is the assumption that you get these half-period out-of-phase type solutions only if there is symmetry. And what I wanted to point to is that after a number of years of working on this, there's finally a theorem. And the theorem says that if you have a coupled system of differential equations, a network of differential equations, and the network is transitive. That means you can get from any point in the network to anywhere else, any other node, by a sequence of connections or couplings. Then a periodic solution with phase shift synchrony that is rigid in the sense that if I perturb the differential equation associated with the network a little bit, the periodic solution will perturb a little bit, but you'll have the same phase shift synchrony. That can only occur if there's a symmetry. The symmetry may be of something we call a quotient network, but it'll be a symmetry in the network structure that actually forces this. So I'd like to think of these examples as being very nice ones for going back and forth between mathematics and biology. A number of people were involved in this. I mentioned Luciano Buono, Jim Stewart, and Jim Collins and Ian Stewart on the Gaits. The general phase shift synchrony results with Ian Stewart and a couple of postdocs at MBI, David Romano and Yunjia Wang, and the rivalry, again, amongst several of us at MBI. I also like to point out that we found out about the binocular rivalry when Hugh Wilson came and gave a talk about it at MBI. So that was a lot of fun. Anyway, thanks a lot.